again, when we start talking about other solar systems outside our own solar system, we're actually starting to develop the capability to be able to see some of these planetary solar system disks that are forming around other stars. So here's a case, Beta Pictoris, where we're looking down to something like the scale of Pluto's orbit, and we're actually starting to see things that look like, sort of like planetary disks. Okay, again, at artist conception, bipolar outflow. Let's see if I can do this one to work. It might not, but I'll try. And probably again, I'll just run that one just for the last one. Bipolar. There. So you might think it's a bunch of people with some kind of a problem, but okay. But in this case, bipolar has a completely different meaning. Let's go full screen with this. Okay, so this is a disk that we're talking about.
This animation shows a protostar and surrounding disk in which planets might form. The wind of the young star tends to form bipolar jets perpendicular to its disk, ridding itself of excess energy.
So these are called bipolar outflows because they're going out of the North Pole and the South Pole, so to speak, of the center of the disk there. And we think that that kind of an outflow plays an important role in allowing some angular momentum to escape from the forming sun. Because as we'll see in a moment when we talk about the sun, it's actually spinning much slower than we would expect the sun to spin. And this kind of outflow may be one way that angular momentum is actually escaping from the early sun. To allow it to slow
Eventually,
down.
the area swept mostly clean around the newborn star. After several tens of millions of years, the star is seen alone, perhaps along with any planets that did manage to form.
Okay. Just another example of a disk of planetesimals around another young star. Not very well resolved, clearly, but we have new missions that we're going to use to try to follow up the Kepler observations that we're doing now, to try to discover new planets that could be in habitable zones, what was really interesting. Okay, so the theory that we've been talking about was originally the nebular model, now it's the condensation model, and it actually is able to account for a lot of the general regularity and the pattern that we've seen in the solar system. It generally forms a small number of isolated planets. Well, that already is important because, if your model forms 100 planets, it doesn't look anything like our solar system. So you want to form planets in an isolated way. The condensation model does that. It also successfully accounts for the circular orbits that we see with very low eccentricity. Most of the planets' orbits are in the same plane, in the same direction, the same direction that the sun spins, and the planets actually spin in their daily motion in the same direction that they orbit. That's the general pattern. Moons orbit in the same direction as the planet spins. We can account for the differentiation of the solar system. We can account for the differences between asteroid and comet and planetary bodies and the locations of the comets. So this is all general regularity, right? And then on top of this, there are exceptional things. So we also see some exceptional things and pretty much universally appeal to a catastrophic event to explain this kind of a deviation from the regularity that we see in every other way. Retrograde spin of Venus, which means that we see Venus spinning counterclockwise as viewed from the north celestial pole, right? We see the 98-degree tilt of Uranus's orbit, and we see the moon Miranda there having this really weird configuration, probably because of fused collisions. Spin orbit resonance of Mercury actually is related to a collision because remember that we have to get that big mass in the Caloris basin so the sun has something to grab hold of gravitationally to enforce the 2 to 3 spin orbit resonance of Mercury. So even something as relatively obscure as that actually implies an ancient collision. And the formation of our moon, right? Formation of the Earth-Moon system also seems to have required a collision between the Earth and a Mars-sized object in the distant past. All right, so the sun contains by far most of the matter in the solar system, but it actually only contains 0.3% of the angular momentum, which is the momentum associated with spinning motion. So that, on the face of it, is a very bizarre contrast between those two numbers. How could it have most of the mass, have been living in the center of the solar system? It should have been spun up the most, if you think about how that would work. Objects that have smaller radii tend to spin up faster and get to higher spin rates in order to conserve angular momentum. So why would it only have 0.3% of the angular momentum? On the other hand, Jupiter contains 60% of the angular momentum in the solar system, even though it's about 1,000 times less massive than the sun. So we deduce from that the sun probably was spinning much faster early on, and some angular momentum was probably lost by the solar wind, or maybe a bipolar jet of the kind that we were just talking about. All right, so we've actually spent a little bit of time talking about detection of other solar systems. We use Doppler shifts of host stars. We also look at planetary transits, which the Kepler mission is doing. And we're hoping that we'll actually be able to eventually detect planets around solar-type stars. And we're actually on the verge of doing that. There was a study about almost a month ago that was published that made the claim that there were maybe 100 or 200 billion Earth-type planets in the habitable zone in our own galaxy. Now, there's probably about 200 billion stars in our galaxy, so if you start talking 200 billion Earth-type planets, that's an average of around one per star. That's an incredible thing, but the way that they actually achieve that isn't by directly detecting the planets. It was actually by using a kind of indirect type of detection event where they actually used two different methods. One tended to detect planets that were close to the star. The other method tended to detect planets that were farther away. So they got two numbers, and they just connected them with a line to figure out what would be in between at Earth distance. And they came up with this incredible number of 100 or 200 billion. So again, depending on your religious view, pretty hard to believe that we would be the only planet on which life would form, but until we have one other example, we have no way of really computing those odds. Okay, so this is just an example of how we would see the blue shift, red shift, Doppler shift. And this is the variation in radial velocity, which is what we deduce when we look at the shifts in the spectral lines. So this is a particular system, 51 Pegasi, which has one planet there. Another example of the types of curves you see when there's multiple planets, because here you have multiple planets that are pushing the star around in slightly different ways, and you can deduce that there's actually 3 planets in that particular system, Epsilon and Andromedae. But notice that these planets, there actually is one sort of around the orbit of Earth, around 1 astronomical unit, but these tended to be giant planets, it turned out, because the Doppler method tends to pick out very massive planets, because they're the ones that are going to push the star around more gravitationally and create the Doppler shift. Okay, so that brings us finally to chapter 16, the sun. So already just looking at this picture, we're seeing some things that we may not have known about the sun. I mean, obviously we know that the sun has this yellowish disk that we call the photosphere, and probably most people know that the sun has these dark spots called sunspots, but not everybody necessarily knows that there's this really, really bright, super hot region outside the visible disk that's called a corona and the chromosphere, which, again, are actually the regions that cause problems if you look at a solar eclipse without proper protection. Because when you look at a solar eclipse, what happens is the moon blocks out the yellow disk of the sun, but the moon does not block out the corona. And the corona is so hot, millions of degrees, that it actually emits a lot of ultraviolet radiation. And because our eyes are not sensitive to ultraviolet radiation, when we look at this, we're seeing a blinding flash of ultraviolet radiation, but we don't close our eyes because we don't see ultraviolet radiation. But it drills into our retinas just the same and causes damage to the cones and rods in your eyes. So that's the actual reason that we must not look at a solar eclipse with the unaided eye. You can do it. You won't instinctively look away, but you can blind yourself because of the emission from the very hot gas outside the yellow disk. Okay, so the sun is basically a pretty low density object. We'll see that it's actually got a density close to the density of Jupiter. A hot, glowing ball of gas. no solid atmosphere, no solid surface anywhere in there. If you could somehow land on the sun and cruise down through the solar atmosphere, you'd never reach any solid core at all, and you probably wouldn't last too long, either on your way down there. As I mentioned a moment ago, there's a chromosphere and corona. We'll talk about what exactly each of those means. And they're above the photosphere. The photosphere is that yellow disk that we look at when we see the sun. That's what we call the photosphere. The reason we call it the photosphere is because it's basically the surface from which the photons that we see is actually generated. It comes from that actual surface called the photosphere. Not a solid surface, but it's a surface from which the photons tend to be created that produce the radiation we see. And then, if we go farther out in the corona, we see that it actually turns into the outflowing solar wind. Okay, so here's a cutaway view of the sun. There is a core, about 200,000 kilometers across. So that already is like, several times larger than Jupiter, just the core that we're talking about. Overall, the sun is about 10 times larger than Jupiter, about 100 times larger than the Earth. So that radiating core in there is the most active part of the solar system by far. Actual nuclear reactions taking place in there. And outside the core, where the nuclear energy is generated, there's a region where the energy is carried away by radiation, and then there's a region above that where we have overturning motions and the energy is carried away by convection. On top of the convective zone, we have the photosphere where the visible photons are generated that we see. Now, it's interesting to note that the energy that's being generated in the core is creating an outflow of energy. And that outflow is the same rate at every radius inside the sun. So we have, like, if we want to talk about what we call CGS unit, there's about 10 to the 33 ergs per second. The erg is about the energy of a housefly flying around. If a housefly ever bumps into you, you've just been hit by about an erg of energy. Okay? But the solar core is generating 10 to the 33, a 1 followed by 33 zeros, ergs of energy every second. It has for billions of years, and it will for billions of years more. And that amount of energy comes out of that white area in the center due to nuclear reactions. It gets fed into the radiation zone, and at the top of the radiation zone, you still have that same amount of energy coming out, but it's in a different form. Goes into the convection zone. We have this overturning motion like a boiling pot of water. At the top of the convection zone, the amount of energy coming out is again 10 to the 33 ergs per second. So we're just seeing energy change form, but it's the same rate of progression as it moves out. So what that means is that the radiation, what we call the luminosity, the total brightness of the sun in the visible light, is actually exactly equal to the rate at which energy is being generated in the core.